Hello everyone, thanks for showing up for this talk. In this presentation, I will introduce an improved approximation algorithm for MMS allocation. Let me first introduce the problem. We have a set of agents, a set of indivisible items where they cannot be cut into pieces, and additive valuation functions for each agent. By additive, I mean if Vij is valuation of item j for agent I, then the valuation of set S is the sum of valuations of items in this set. And for output, we are looking for a fair allocation. So what is a fair allocation? First, I will define the notions of fairness for divisible items. One of the notions is proportional allocation. An allocation is proportional where each agent likes her own bundle at least the average bundle. The other notion is envy-free allocation, where each agent likes her own bundle at least as much as other agents' bundle. An algorithm to find an allocation which is both proportional and envy-free is cut and choose protocol. Let me show you with an example. Let's say we have a cake and two agents. I ask the first agent to cut the cake into two pieces where she equally likes each piece. And then I ask the second agent to choose her favorite piece, and I will allocate these pieces accordingly. It's easy to check that this allocation will be both proportional and envy-free. But when it comes to indivisible items, these notions might not always work. Let's say, for example, if I want to allocate a diamond and a potato among two agents, no matter how I allocate them, this allocation will neither be proportional nor envy-free. So this made a need to define a new notion for fairness of indivisible items. Budish in 2011 defined Maximin share allocations, which has the same essence of cut and choose protocol. I will show you with an example in this slide. So let's say we have two agents and 5 items, and these are the valuations of each agent for each of these items. Then we ask the first agent to partition these items into n bundles, where n is the number of agents, such that the valuation of minimum bundle is maximized. This has the same idea as cut and choose protocol. Now we call the value of this minimum bundle MMS value of this agent. We repeat this process for the second agent and remaining agents. And if we go back to the definition of MMS allocation, an allocation is MMS if each agent likes her own bundle at least her MMS value. This is an example of MMS allocation. If you look at the main table, agent 1 is getting 9, which is more than her MMS value, and agent 2 is getting 13, which is also more than his MMS value. So to be on the same page, this value, which is value of the minimum bundle in this partition, is MMS value. The partition, which is specific for each agent, and he values each of these bundles at least his MMS value, is called MMS partition. And this allocation that gives everyone at least their MMS value is called MMS allocation. Finding MMS value is hard, so it is finding an MMS allocation. But in the previous work, it has been shown that finding a PTAS for finding MMS value exists. Also, it has been shown that MMS allocation does not always exist. So this made the researchers to look for alpha MMS allocation, where each agent gets at least alpha times their MMS value for alpha smaller than 1. It has been shown that 2/3 MMS allocation always exists, and in the groundbreaking work, it has been shown that 3/4 MMS allocation always exists. They also showed a p-test for finding such allocation. However, their proof was rather lengthy and complicated. In this work, we proved the existence of 3/4 MS allocation in a much simpler way. Our proof was simple enough to extend it to two results. First, for the first time, we showed a strongly polynomial time algorithm for 3/4 MS allocation. Second, we showed the existence of a better bound for MS allocation, 3/4 plus 1/12n, where n is the number of agents. This will also result in a PTAS for this factor. I will mostly focus on the first result, which is simpler to explain, and it is the base for our other results. So the challenge for finding MMS value, it's the high-valued items. Let me show you why. So imagine if in an instance, we have the value of items, the total value of items is n, which is the number of agents. And this can be obtained because MMS allocation problem is scale-free. This also implies that MMS value of agents is at most 1, because MMS value is value of a minimum bundle in a partition. Also, imagine if the value of all items for all agents was 1/4, at most 1/4. Then we can do a backfilling and give everyone a bag with value at least 3/4, which is also at least their 3/4 times their MMS value. Let me show you why with an example. So let's say this is a set of agents. We start with an empty bag. We keep filling the bag with items one by one until someone likes it more than 3/4. And then we allocate this bag to this agent. If there are multiple such agents, it doesn't matter. We can allocate it arbitrarily. Now look at this bag. Before adding the last item, no one liked this bag more than 3/4. Adding the last item will not increase the value of this bag by 1/4, by more than 1/4. So together, the value of this bag for all remaining agents is at most 1. So now we have n-1 agents with the value of remaining items is at least n-1. So we can repeat this process and give everyone a bag with value 3/4, which is also at least 3/4 times their MMS value. So if the value of items for all agents was low enough, we could easily give 3/4 MMS allocation. So this was the challenge about the 3/4 MMS allocation. Let me tell you some nice things about this problem. First, MMS allocation problem, as I said, is scale-free. Also, without loss of generality, we can assume that order of preferences over the items is same for all agents. So let's go back to our example. Now, if I define a new instance with 5 imaginary items, where the valuation of item 1 is the value of the favorite item of each agent, and the valuation of second item is the value of the second favorite item of each agent, and so on. And as you can see, I have ordered the valuations in each row. Now, it can be shown that the MMS value of this instance is same as MMS value of this instance. And if I find 3/4 MMS allocation for this instance, we can also find 3/4 MMS allocation for this instance. The intuition behind this is there are more conflicts among agents in this instance, and it's a harder case. So without loss of generality, I assume that item 1 has the highest value, then second is item 2, and so on. The third nice property of MMS allocation is valid reductions. Imagine if there is a set of items S in M and an agent I star, such that agent I star likes this set at least 3/4 times her MMS value. And also, if I find the MMS value of the remaining agents for remaining set of items, and this value is at least their old MMS value, then I can allocate item S to this agent and find 3/4 MMS allocation for this new instance, and it will imply a 3/4 MMS allocation for the original instance. So this will help us to reduce the size of instance by allocating some items to some agents. Now, in our algorithm, we assume that MMS is known for all agents. Then we scale the valuations such that MMSI is 1 for all agents. And this will also imply that the total value of items is at least n, which is the size number of agents. Then in step 1, we do some valid reductions. And step 2, we'll do a generalized backfilling, which is similar to the backfilling that I showed earlier, but it has more details. So in this paper, we do 4 different valid reductions. First, if someone likes item 1 more than 3/4, we can assign it, which is the highest valued item. If someone likes item n and n plus 1, we can assign it. If someone likes item 2, 2n, and 2n plus 1 more than 3/4, we can assign it. I mean, if someone likes item 1 and item 2n plus 1 more than 3/4, we can assign it. I will prove the second valid reduction. I will show the proof scheme. So let this be a partition of MS partition of some remaining agent, where all value at least 1 for this agent. Now, by pigeonhole principle, there will be 2 items in a bundle from item 1 to item n plus 1. Here, or from item 1 to item 4, which is this bundle. Now, I will show a new MMS partition with n-1 bundles which all value more than 1 after removing item 3 and item 4. So in this bundle, I will replace these 2 items with item 3 and item 4. So you can see I have replaced item 2 and item 4 here. And if there is any remaining items, I will allocate it arbitrarily. Now, I haven't changed the value of this bundle. And the value of this bundle has only been increased because item 2 has more value than item 4. And I can allocate this bundle. Now I have found the MMS partition for n-1 agents after removing these 2 items, and they both value more than 1. So this is a valid reduction. Valid reductions will give us very nice structure for the valuation of items, which I explained in the next slide. So after valid reductions, if there's no valid reduction possible, if this is the set of items, for all agents, we have these properties. The first n item will value less than 3/4 for all agents. The second n items will value less than 3/8 for all agents. And the remaining items will value less than 1/4 for all agents. Then I will make n bags with the first 2 n items in this order. And now imagine if the value of these bags was less than 1 for all agents, then I could do a backfilling because I would start with a bag. If someone likes it, I would assign it. If not, I would have filled it with smaller items, with these items, which all value less than 1. And before adding the last item, no one likes this bag more than 3/4. Adding the last item will not increase the bag by 1/4. So together, no allocated bag will have value more than 1 for any of the remaining agents. And since the MMS value has been assumed to be 1, the total value of items is at least n. So I can do the backfilling and give everyone a bag with value 3/4. But the problem is, if assume that this bundle has value more than 1 for some agents, I'm sorry, imagine this bag. The value of the bigger item can be very close to 3/4, and the value of second item can be very close to 3/8. Then together, the value of each of these bags might be very slightly more than 1. So if for an agent, all these bags are value less than 1, or at most 1, then this agent is ready to for the bag filling algorithm. But there are problematic agents where they value at least one of these bags more than 1. So if we study these agents more carefully, we can see that this is the bag with value more than 1. She doesn't like the smaller item more than 3/4. It means that she has to like the bigger item at least, more than 5/8, which means that she likes the first item, which is the most valued items, more than 5/8. Also, after value deductions, we know that no one likes item 1 and item 2 and plus 1 together more than 3/4. It means that all problematic agents like item 2 and plus 1 and all other items here less than 1/8. Also, we study these problematic agents more carefully. We define Li for each of these agents I to be the bags, set of bags with value less than 3/4 for this agent. And let Bi be the set of bags with value more than 1 for this agent. Then we also show that if Xi is the least total value needed to make all these bags in Li exactly 3/4, then we prove this, that if the value of the small items, item 2 and plus 1 to m, is at least this value, which is Xi that I define here, and the number of bags in Li over 8 minus 1/8. If I prove this bound, then I can show that the backfilling will go through even for these agents. And fortunately, this bound can be proved by using the assumption that MMSI equals to 1 for all agents. Now I will show how we extended to our other results. First, we show, now you saw that we can show the existence of 3/4 MS allocation by assuming that MS values are known. Then if we use this bound, Vi of m over n, as upper bound for MMS value of agents, and study this problem more carefully, we can get a strongly polynomial time algorithm for 3/4 MS allocation. Then if we do more careful analysis on this problem, we get an existence of a better bound, 3/4 plus 1/12 and MS allocation. And if we use the PTAS known in the literature to approximate MMS value, we get a PTAS for this vector. Now, if we want to extend our results for 4/5 MS allocation, the issue is number of high-valued items. Instead of 2 and high-valued items, after value deductions, we will have 3 and high-valued items, which are harder to handle. This will finish my talk here. Thank you very much for listening.